Alright, in this video, we're starting a new part of the class. We're going to talk about inner product. What I'll do today is I'm going to look at what we had in RN, something that we haven't used yet in all of this course, and we're going to see what we liked about it, what we did with it, so we know what we're after for general vector space. So let's look back at the dot product. For any two vectors, in any Rm, in any Euclidean space, we had a dot product. So let's say V is A1, A2, AN, W is B1, B2, Bn. We just multiply the matching entries and then we add up the products. Alright, so that gave us something in R, it gave us a number, and that number was interesting in a bunch of different ways. The first way we use that number was to look at lengths. Alright, so one thing we saw was that the length of V squared was V dot V. And so the length of V was square root of V dot V. And we did a bunch of examples of using dot products to compute lengths of combination of vectors, of linear combination of vectors, because the dot product acts nicely with the operation of the vector space. So that's going to be nice here as well. Then another thing we did is we used the dot product to define angles, or to compute angles. So for any VW in Rn, what we had was that the dot product was the length of V, length of W, and then we have cos theta, where cos is applied to the angle between V and W. And if we take the angle between 0 and 180, then we can actually get theta. Of course, as long as V and W are not the zero vector. If one of them is zero vector, we don't really have a direction, and then we can't really compute the angle. In fact, the length would be 0. We get our cos of 0 over 0. And nobody knows what that is. So one of the things we got out of this, that we kept using in proof after proof after proof, was one special case here. So if I have that V and W are perpendicular, or have an angle of 90, well, 90, this would become cosine of pi onto a cosine of 90, that's 0, so I get 0. In fact, this is an if and only if V dot W is 0. Alright, so that was super helpful in trying to figure out the positions, the relative positions of lines and planes. It was helpful in proving geometric properties of triangles, parallelograms, and all of these things. So this is something we use tons. And the final thing that we really liked about having a dot product is the fact that it allowed us to define projections. So we had projection on a direction of a vector. So we have the direction D, we have the vector V, and we looked at the green vector, that's the component of V in the direction of D. So this is the projection. And we also have the orthogonal component. That would be the blue vector. So we found in linear 1, we actually derived this formula. We got that it was V dot D over length of D squared. That's a number you multiply by D that tells you how to stretch your D. So we really liked all of these things. They led us in tons of interesting directions, and we want the same thing for a general vector space. We'll want the same idea for polynomials, for functions, for matrices. And so what we need is to define some sort of product on general vector space. So we'll call them inner products. So let me put it right here. So for any pair of elements in V, I want to define the product of V with W. So if I have V and W in some vector space V, I want VW in R and I'll want to figure out exactly which properties this product should have so that we can do the same thing we were doing in Rn with the dot product. So we'll list the properties, but our goal so we want lengths So we'll want lengths of arbitrary element in a vector space. We'll want angles between elements. And we'll want projections. We'll want projections, but more than a projection like this. This is a projection in some sense in this direction, so on this line. We'll want projection on any subspace we have. So projections, any subspace, W. Alright, so that's our goal. So we'll want this product, and we'll want properties. So just like when we went from vector space Rn to general vector space, we listed what were the nice properties that we'll assume we have so that we can do spans as subspaces, so we can do bases and all of these things. We'll have the same thing here. We'll need certain facts, otherwise we'll get stuck trying to build these things and trying to prove they have the right properties.